Let us move to the second example, where again first we will try to find the pointwise limit using limit theorem, and then we will verify using definition, and then we will quickly look at the graphical illustration just like the previous example. So, here we consider the sequence of functions, So, Fn, where say we define Fn x as each term of the sequence as x cube by say n square for each x in R. Now, we need to find what will be the pointwise limit, and again we have to check using definition. So, first of all, let f of x equal to 0, or let f of x be equal to 0 for any x in real number R. We shall show that this function is the pointwise limit. So, again we know limit 1 by n square equal to 0, right. Thus, using limit theorem, for sequences we have limit f of n x, this becomes limit x cube by n square, which becomes x cube limit 1 upon n square, which is equal to x cube into 0, which equals 0 for all x in R. So, as per the limit theorem, f x equal to 0 is our pointwise limit. Now, again we will try to verify using definition. So, we just need to show that there exists a positive integer n, right, such that mod of f n x minus f of x, this is less than epsilon for all n greater than or equal to capital N. That is, in this case we need to show that x cube upon n square, this is less than epsilon for all n greater than or equal to n. We need to show that such an n exists, right. Now, if x cube by n square, mod of x cube by n square is less than epsilon, this happens if and only if x cube mod of x cube by n square is less than epsilon, which happens if and only if n square is greater than mod of x cube by epsilon, right, and which is true only if n greater than root over mod of x cube by epsilon. Since epsilon is arbitrary, I do not have to use root over epsilon. Now, we choose n to be the least positive integer such that capital N is greater than root over mod x cube by epsilon. Then we have for epsilon greater than 0, x cube upon n square minus 0 is less than epsilon for all n greater than or equal to capital N, where my capital N is strictly greater than root over, or it is a least positive integer which is strictly greater than square root of mod x cube upon epsilon. Now, let us look into the graphical illustration. That means, we shall try to observe that the function f x equal to 0 is also a pointwise limit of the given sequence of functions via graphs, right. So, the given sequence of functions is the sequence of functions is x cube by n square, right. So, that means the term of this sequence are x cube by 4, x cube by 9, right, x cube by 16 and so on. So, first we shall draw the graph. So, the first term of this sequence of function we have f1x equals x cube, right. So, this is the graph of f1x. Now, the second term of the sequence is x cube upon 4. So, the graph of that function would look something like f2x, and so here we will have something like this. The third term of the sequence will look something like this, the fourth term something like this, and so on. So, it is quite easy to observe that this sequence of functions f1x, f2x, f3x, f4x and so on, they converge to the pointwise limit f of x equal to 0. However, we shall try to observe this using the previous method. So, first we have a basic geometric construction. So, as done previously, let P be a point on the x axis, right. That is, P is a point on the line, say somewhere around here. Here we have P. So, P is a point on the line y equal to 0, and let A1, A2, A3 and so on be points on the graph f1x, f2x, f3x and so on. So, if we look closely here, so it might not be possible to draw A1, but this is my A2, here we have A3, here we have A4 and so on, right. Now, again draw two straight lines, y equal to 0 minus epsilon and y equal to 0 plus epsilon. So, the line that we draw is, so say we have, this is my line y 0 plus epsilon, and here I might have, so here is my line 0 minus epsilon, right. So, what we are trying to observe here is that all the sequence of function converge to the limit f of x equal to 0. So, we have the following observation, just like in case of the previous examples. So, observe that the distance, so the distance p a1, though we do not have a1 in our graph. So, still the distance p a1, p a2, just like in case of the previous example, p a3 and so on, these converge to 0. That is, the sequence f1x, f2x, f3x and so on, this sequence, it converges to 0 whenever the point P is on the x axis, right, or we can say that for the point P on the x axis, right. So, for a particular value of x, this will converge to the limit function 0. Now, see that for the present position, P on x axis, observe that mod of fn x minus 0, the limit function 0, this is less than epsilon, and this happens only when after capital N equal to 3, right. If we look at the graph, so here all these functions are, all the fn x minus 0, the limit function, this is our limit function. So, the distance between them is less than epsilon only after the third term of the sequence of function, right. So, here we have n equal to 3, but if we look closely in the graph, if I move my p to the positive direction of x axis, say somewhere around p dash, or say p dash will go somewhere around, say here p dash, then I might find that my value of capital N will change, right. In all the cases, that means for each particular value of x or each particular point P, they fit, in all the cases they fit exactly to the definition of pointwise limit, right. So, what was the pointwise limit? That is, there exists a positive integer n such that fn x minus f of x, this is less than epsilon for all n greater than or equal to n, which is true for each value of x. So, also graphically we have seen that it is clear that this value of n, the value of capital N, that depends upon the position of P, right, upon the position of the point P, or we can also say that that is the value of x. It is not an easy task to find the pointwise limit of sequence of functions using the graphs for each function. However, we shall use the limit theorem to find the pointwise limit as discussed previously in both the examples. So, we have certain more examples where we have discussed this in much detail, where we have found the pointwise limit or whether the function converges pointwise to a function f or not. So, the third example that we have, so here we consider the sequence of functions fn on say on an interval say 0 1, where fn is given by fn x equal to x power n. Now, as we have seen in the graphical illustration, the sequence of functions converging to a pointwise limit depends upon the position of p, that is the value of x. So, we have to be careful that what x we choose before finding the pointwise limit. So, in this case, first we have if x equal to 1. So, then what does our sequence of function becomes, right? So, then I can write each term as fn x, each terms becomes as fn 1, which is nothing but 1, right, 1 for all n. That means, that is this sequence fn x is actually is the constant sequence, is the constant sequence 1, right, and we know the constant sequence 1 converges to 1, right. Therefore, in this case limit fn x equal to 1. Now, if x lies between, or say if x lies between 0 and strictly less than 1, then my sequence of function fn x will become x to the power n, where x is less than 1 and just greater than 0. We have discussed this in sequence of real numbers, that this sequence converges again to 0, right. So, thus we can write that limit fn x, this is nothing but equal to 0. So, as you can see, we have two cases. First, for x equal to 1, we have a limit 1, and when x was between 0 and 1, we have a limit 0. So, how will our pointwise limit look like? So, we can say that therefore, limit fn x, the sequence of converges, the sequence of function has a pointwise limit say f x, where f of x is given by so this function is 0 if x lies between 0 and 1 if x equal to 1. So, this, that means we can also say here, we can write that the sequence of function fn converges pointwise to the function f x, or we can say that the function f x is a pointwise limit of the sequence fn x, or as already written, we can also write that limit of fn x equal to f x. Let us go to the next example. So, example 4. So, consider the sequence of functions fn, right, on R, where each fn is given by the formula fn x equal to mod of x 1 plus 1 by n. Now, again, since we are aware that the limit function depends upon the value of x. So, we have the following two cases. If now note that here the sequence of function is defined on the whole set of real numbers, right, unlike the previous case where the sequence of function was defined only on a closed interval 0 to 1. So, if x equal to 0, it is obvious that fn x becomes fn 0, which is nothing but 0 for all n, that is, it is a constant sequence 0. So, in this case I can write limit fn x, this equals 0. Again I have another case, if x not equal to 0, then I can write limit fn x. So, if I need to find the pointwise limit, I need to find this. So, limit mod of x 1 plus 1 by n. So, as n tends to infinity, this sequence converges to mod of x. Thus, in this case we can say that limit f n x, the sequence of functions, equal to f x, where my limit function f of x equal to mod of x. Let us consider another example. So, here we have the sequence of function again, consider the sequence of functions fn. Now, this is defined on the whole set of real numbers, where my fn is given, or sequence of function is given by the formula fn x equal to 1 by 1 plus x to the power twice n, right, for x in R. Now, here we have the following cases. First, note that if x lies between -1 and 1, then limit x to the power twice n equal to 0. If x equal to plus minus 1, then clearly limit x to the power twice n equal to 1. The case left to handle is if x is greater than 1 or x is less than -1, then limit x to the power twice n equal to infinity, right. So, for the sequence of function, we therefore have the following cases. We have the following cases. So, the first case that we have is if x lies between -1 and 1, then limit fn x equal to limit 1 upon 1 plus x to the power twice n. Since we already know the limit of x to the power twice n, so here it is easy to find that this is equal to 1. The second case that we have is if x equal to plus minus 1, then limit fn x, again similar to the previous case, we can clearly see that this is equal to half. The third case that we have is if x strictly greater than 1 or x strictly less than -1, then clearly since limit x to the power twice n tends to infinity or converges to infinity, then we can say that limit fn x equal to 0. Thus, limit fn x equal to f x, where now my limit function f of x is given by is given by f of x equals, so we have the cases that it is 1 if x lies between minus 1 and 1, is half if x equal to plus minus 1, and 0 if x equal to 1 and x tends to minus 1. So, now we have the pointwise limit as f of x equal to this, right. As we have seen in these examples that the limit function or each of the sequence of functions has a different limit for each different values of x. But sometimes it so happens that the limit function or the sequence of function converges to a limit without depending upon the value of x. So, such type of sequence of functions are said to be uniformly convergent. So, in the next module we shall discuss uniform convergence and discuss certain criteria to check whether a given sequence of function is uniformly convergent or not, including with certain tests. Thank you.